Today we have with us Miguel Encinar. Thanks for being here today.
Thank you.
Miguel did his PhD in aerospace engineering in the School of Aeronautics at the Polytechnic School of Madrid under the guidance of Professor Jimenez, who was also one of our speakers a couple of years ago. He then moved to Johns Hopkins University for a postdoc, and recently he has joined us at the aerospace department as a visiting professor. And well, his research, I guess we're going to see today, has to do with fluid mechanics, numerical fluid mechanics, dealing with high performance computing and GPUs. And I think it's fascinating. See what you have to tell us today. So nothing else. Thank you very much for being here, Miguel.
Thank you, Manuel, for the introduction. Thank you, everyone, for coming. So for this talk, I'm going to delve a little bit on computing and turbulence. And well, first, I'd like to thank the university for giving me this opportunity to give this talk. And I will also, I didn't include an About Me section in the talk, but I just want to mention that I work here now. So if you have any questions or you are interested in learning more, you can always knock on my door, okay? Or if you are not from here, you can always send me an email. So, well, based on the title, you may have guessed that I'm going to talk a little bit about computers and turbulence. First, I would like to clarify what they mean for me. So for me, turbulence is a problem. It's the physical and engineering problem I'm trying to solve. And for me, computing is a tool that I use to solve this problem. So we don't do very complicated numerical algorithms. We don't try to milk computers as much as possible, but we try to solve turbulence. And for this, we found a very useful tool that are computers. The reason I'm talking about both in this talk is because I feel that turbulence is a very particular problem of me that maybe is not for interest of everyone, but tools are very useful to everyone. Everyone wants a tool that helps solving their problem. So even for me, the order is this, and for me, turbulence is the thing I really care about. I'm going to talk also a little bit about computers because I think it's the most transversal topic I have to offer. So let me introduce what turbulence is and why it's a problem. So turbulence, most people have this notion, is a seemingly random movement of fluids. It's not actually random, that's why it's seemingly is in red. It's actually chaotic. So turbulence is deterministic, and in principle you should be able to predict turbulence, but it's very complicated, okay? Where you can find turbulence is everywhere, okay? If the Reynolds number is high enough, which means that the flow is moving fast enough, you can find turbulence everywhere. And many of these problems are of interest to the aerospace industry. From the left to the right, there is a higher Reynolds number, higher and higher, but in flows in pipes, you can already find turbulence. You can find it on the wakes of planes and on the wakes of boats and submarines. That's a very hot topic now. Wind farms are also a very active topic now of research in the aerospace community, and you can find turbulence is a huge problem because the wakes of the wind turbines are turbulent, they interact with each other, and it's something that, for example, we don't know about. And all this is happening in the atmosphere, which is also a turbulent flow. And if all that is not big enough for you, you can always find bigger turbulence by moving far away, okay? And I would also like to comment a little bit on the why turbulence, because it's something that is not very well understood. But the legend says that Heisenberg himself wanted to ask why turbulence, and he wasn't sure that God would know the answer, okay? And the idea to me is that it's normal that we have turbulence because the flow is allowed to be turbulent. So for example, this is a video of a flow where the momentum has to go from right to left. And when the speed is small, it goes in a laminar way. And when the speed gets higher, it becomes turbulent. But the momentum is still going from right to left. So it's satisfying the boundary conditions. However, because the fluid particles are able to interchange momentum, they have those degrees of freedom, they can do it in a complicated way. And this is common for most physical devices. So this is a double pendulum, which is some of the simplest chaotic process that you can have. It has 4 degrees of freedom. And it has no energy, as in the left. It moves very smoothly. It has a predictable path. But if you give it enough energy, it can move in a complicated way, and it does so in general. And this is the standard behavior of physical system. If you have enough degrees of freedom and energy, you do funny stuff. If you have carbon, for example, this is a very cheesy example, but I'm going to use it. If you have carbon and you have a few molecules and a little of energy, you can form hydrocarbons. But if you have a lot of carbon and a lot of energy, you can create a platypus. And I don't believe anyone can from the chemistry of carbon predict that you're going to find a platypus, but you find them. And the reason is that you have all those degrees of freedom. And that is in essence why turbulence is complicated, okay? So explaining a little bit why turbulence is important is one of the few open problems that we have from classical mechanics. You don't need relativity or quantum to be complicated. Even in classical mechanics, if you have many degrees of freedom, it's complicated. I want to mention that one of the lastest Nobel Prizes in physics was awarded to someone, which is Giorgio Parisi, who did a lot of work in turbulence, okay? I had to read a few of his papers for my thesis, so I'm very happy about it. And it's something that is important for the scientific research. It's also important from a practical point of view. Turbulence in the estimation, depending on where you read it, is about that 5 to 10% of the energy of the humanity is expended in either pushing flows through pipes, like fuel in a pipe or gasoducts, that consumes a lot of energy, or vehicles in the atmosphere or in the sea, and that also consumes a lot of energy. So in total, it's something that we would like to understand well. Why is complicated? To these degrees of freedom that scale with the Reynolds number to the 4 squared, you have to add something else that I wanted to go here, that is scale separation. When you have a turbulent flow, the difference between the largest scale that you have to care about, which by eye you can see that the white patch and the black patch are approximately the size of the slide. And the smallest thing, that is like the smallest filament that you can see there, is very high. And you have to model and account for all these degrees of freedom to be able to have a successful model of turbulence, at least in principle, okay? And this doesn't happen always. So here, this is an example of another physical model which is a gas, like the air in this room, which has a lot of degrees of freedom. There are millions. Million is a very small number for the number of particles of gas that there is in this room. And we have a model of that, which is called a thermometer, that works very well. It works very, very well at estimating the average kinetic energy of the gas. And we say that that model coarse grains very well, that we can do a reduced model with few degrees of freedom that works very well. You cannot do that for turbulence. And the reason is that in this case, all the degrees of freedom are the same, and in turbulence, all the degrees of freedom are not the same. So if you try something naive, it won't work. That is an example, one of the very early visualizations of a mixing layer, and you can see that there are structures there of the order of the mixing layer thickness that are controlling the dynamics, and they are different from the rest of the flow. And the idea, and what we are trying to do, is that if we understand those motions, in principle, we should be able to say something about the flow without considering all the degrees of freedom. So given this framework, what computers have to do with this? There is also one very particular thing about turbulence. In most problems, you are trying to find the model. You don't have a good model for your engine. You don't have a good model for your plasma. You don't have a good model for whatever physical task you have at hand. But in turbulence, we really have a good model, which are Navier-Stokes equations, model turbulence very well. The problem is that that model is very hard to compute and very costly to compute. So by computing it in research, because we cannot do in a practical way computations of turbulence, the idea is that we can gather enough information to be able to identify these degrees of freedom and to be able to see if we can describe the flow with the help of them. So that is a little bit the idea. And what I'm going to try to convince you is that computers can help us achieve this. So I think everyone has seen at least this once in their life. This is a plot of the Moore's law, which states that the computing power grows exponentially, basically. What actually grows exponentially is the number of transistors. So anyone that was young in the 70s has lived that an iPhone now is more powerful than all the computing power that we have in that time, okay? And everyone has one of their pockets. However, this plot is a little bit of a lie. The real plot is this one, okay? If you see the blue and green line, that is actually telling you the power of a single core in computing. And that has been stale since 2006, approximately. So if you are doing something in a single core, you are actually not growing exponentially your computing power and your capability of prediction. You have to do something else. Now what we are doing is using many cores. Typically, you don't use one, but you use many. There have strategies that have been alive for a long time, which are multi-threading. You use several processors in parallel. And there is one that people are not aware, but that everyone in this room has used, even if they don't know, which is vectorization. When you have a computer and you have a processor, and you have to add two vectors that are very long, your processor doesn't add them one by one. It has them maybe 4 by 4, like in that plot. So by doing that simple trick, you can get 4 times the speed, okay? And now we have a new thing, a new device that is reasonably new, which are GPUs. It's something that looks like this and was used to play video games. But at some point, someone realized that it could be also useful for us doing research, okay? And the idea is that these GPUs are new and we can exploit them for our calculations, and they can help us find answers that were impossible to find before. How this thing works, essentially, is a very, very, very large vector unit. So the thing that I just described, I have 2 vectors and I add elements 4 by 4. Now you can add them 5,000 by 5,000. And this works they are very slow, however. So if adding 1 by 1 with a normal processor is faster than what it takes you to add 5,000, but you add 5,000 at the same time. So these are very good for algorithms that benefit from vector units. So they cannot be sequential. There needs to be something that can be done in batches of very large numbers. 5,000 is a very large number for computing. They have advantages if this fits your problem. They are very cost efficient. So if you look at the performance power that you get per dollar that you spend on hardware, it's unthinkable to get something better. And they are also very energy efficient. So if you are thinking of saving the planet, they are also a very good thing to have, or paying the electric bill. However, there is a price that you have to pay, okay? It's not as easy as plugging one in your computer and everything is a dream now. You have to work yourself because codes don't work directly on GPUs. You have to invest research time on adapting your codes to run them. And what I will like to convince you after this talk is that it's worth it to invest that time because you can do things that are nice. And depending on your problem, there is not a unique way of using GPUs that will fit every problem. Because of this particularity that they are very large vector units, depending on what you're doing, you may need to do one thing or the other. So I'm going to show 2 different cases that have been useful for us. It doesn't mean that they have to be useful for you, but it means that there are many ways, probably more than 2 and 10, that you can think of using them. And maybe this inspires you to find your own way. So the first case I would like to comment is this one. In 2018, with the help of Alberto Vela, that is now here working also as a visiting professor, and Professor Jimenez, we ran a very, very large simulation of a channel flow. It's the things that Jimenez has been doing during his career, which is running a very, very large simulation in a cluster. The reason largest has a dagger is because it's tied to the largest. It's exactly the same size of simulation that we had at the same time. It has 15,000 million degrees of freedom. So it's something that you really benefit from running on GPUs because it has a lot of degrees of freedom. PDEs are very nice candidates for GPUs because a PDE is essentially the same equation for every grid point. So if you have more than 5,000 grid points, you can use a GPU. When you do things like this, what you're doing essentially is using your GPU as a very large CPU. I have a cluster. Before my cluster had CPUs. Now it has CPUs, but I do the same. I don't change my methodology, and I can do the same that I could do before. You cannot run a bigger case by doing this, but you can run faster. And running faster in our case meant running for longer. And I don't know if you appreciate the video, but there are skates there that are very slow, that are running from left to right, that we care a lot because they carry a lot of drag, and we wanted to study them. And having a larger simulation allows us to do that, but with a shorter one is impossible. For reference, this is 4 times longer than what we could do before. Okay? Another challenge that you have when you run 4 times more is that you generate a lot of data. And this will happen also in my second case. And generating a lot of data is very bad because you have to post-process it. So for these cases, and it's something that if you run in GPU, probably you will have the same problem. We have to be clever about how we store the data to be able to reduce. So if you want more details on that, then there is a publication with the co-authors about that. So what can we do from this? With this data, you can do a lot, but what the case I wanted to talk today is that we wanted to see if we could observe the flow, the turbulent flow from the wall. So in a practical application, if you want to know the state of the turbulent flow and you don't have a PIB and you don't have a DNS, your sensors are going to be located in the wall and you may care about the state of the flow for control, predictability, or things like that. And what we did is we decided to see how far we could push a linear model for this task. A linear model, because it's linear, you can close it exactly. in an optimal way. And it's something that looks like this. It has the covariances matrix of the measurements on the left and the cross covariance of the measurements and the velocity field that we have from our DNS on the right. This is something that you can compute with data. For those of you who are doing machine learning and you know about neural networks, this is exactly the same as having a dense layer with no activation, but fully connected dense layer. That means that you have a layer fully connected of 1 million neurons approximately because of the grid resolution. It's something that cannot be achieved at the moment with machine learning techniques. This is the only way of doing it, okay? And we wanted a linear model because we wanted to open it and see what it was doing. At the time, not much people was doing reconstructions, and we wanted to start somewhere. And the good thing is that we found something that it works. So on the right, you have the reconstruction. On the left, you have the ground truth. And that number that is growing is the distance from the wall. And you can see that very close to the wall, the reconstruction is exact or almost exact. And when you're moving farther away from the wall, you start losing things. The reconstruction becomes worse and worse because you're farther away, you're losing information, and you're predicting worse and worse. Even when you're far away, this model is useful. You will see it a little bit later. But the idea is that with this, we have a linear model, it works, you can reconstruct something, and because it's linear and we control it, we can assess the errors, where are they coming from, how are they, and so on. So what we can do is study which measurements of the wall, at the wall produce which errors, and in which velocity components, what can we predict, and what not. And when you do that, what you see is that if you use all the measurements, which are the drag, the pressure, and the drag in the cross plane direction, that one is a little bit weird, but I guess everyone gets the other two. They affect the different velocity components. If you can measure everything, you get predictions that are of the order of the 70% of the stringwise velocity. That is very good because stringwise velocity is related to drag, and about 50% of the Reynolds stress, which is also good because Reynolds stress, for those of you who are not familiar with turbulence, are the things sustaining the turbulent flow. If you remove them, the flow relaminarizes. So if you're thinking on a control problem, what you want to touch is the Reynolds stress. And 50% of them can, in principle, be sensed from the wall with a simple model. And also, one thing that we could do, again, because the model is linear, is say where that 50% is coming from. Because it's not the same having something 50% of the time correct and 50% of the time wrong, or having something that is always 50% wrong. And that is the type of questions that we can answer. And we can answer that because we can open the estimator, which is something that looks like this. This is a matrix that gathers the influence of the three measurements, the pressure, the drag, and the cross drag, to the three velocities, which are the outputs, which are the stringwise, the wall normal, and the spanwise velocity. This is the wall, which is in the top part, and the wall distance moves down. And you see that all these estimating kernels look like triangles. They widen when you move farther away from the wall. And what that is telling you is that you are getting 50% of the energy, not because you are doing everything wrong. It's because you are only capturing things that are large enough to touch the wall. And it's something that you can estimate and measure well. We can even give a semi-empirical law of what can be detected and what not. And this all was possible because we had access to this data. I want to comment that this database is public. Most of you probably don't work with turbulence, but if some of you do, it's something that if you have a model or something that you can test, you can do it. Me in particular, during my thesis, I use this database for another task, which I'm just commenting, which is estimating how much a linear model matches observations in a turbulent flow. And this is something that can be accomplished with this type of data. So I promise you a second way of using GPUs, which I'm going to go now, which is different from this one and probably is more useful to everyone. So in the one that I just explained, for me, a GPU was like a large vector unit. I'm considering it as the substitute of my CPU. And I'm running a big problem using many of them. This is something that few people do. But this second one I feel is more interesting. GPUs have 5,000 cores. That is on the order of what you have in a small cluster. So you can change your way of thinking and think that your GPU is your cluster, is your computing unit. I'm going to run a problem that fits in one GPU. For that, what you need to do is find a problem. You probably need to do some compromises and adapt your problem to run it in one GPU. But that runs very fast because the GPU is like a very small cluster that runs very fast, about 20 times faster typically compared to a CPU application. And 20 times faster is a lot. You can do many things with something that runs 20 times faster. So if you have many of them, for one of the easiest way of using this, if you have a few GPUs, which is something that is accessible in a university, you can run an ensemble of simulation. So instead of running one simulation at a time, you can run 10. You can run 20, depends on your problem. That is very good for most people. You can test many parameters at the same time. You can do uncertainty quantification of the fly. You can test what we did, which is test how your flow behaves to different perturbations. So in a series of papers by my also first postdoc advisor, Jimenez, he did the study of the evolution of localized perturbations in 2D. He could do that by adding many localized turbulences in 2D turbulence because 2D turbulence is a very cheap problem. We could do it in 3D during my postdocs because we had access to GPUs. And one GPU can run a 3D problem very, very fast. So I'm going to talk you a little bit about this case. So we had a flow that looks like that, which is decaying homogeneous isotropic turbulence. It's turbulence in a box, typically called. This number there is the resolution, which is very, very, very close to what is bad. And the reason is that we need to fit this problem in a GPU. And the number of points is contained. For a reference, this has 50 million degrees of freedom. The other one has 50,000 million degrees of freedom. So this is a problem that is 1,000 times cheaper. But I can run the simulation in 1 minute in a GPU. It will be about an hour in our hardware, at least in a CPU. And the Reynolds number is still high. The Reynolds number, even if that number doesn't mean anything to you, is the separation between the blue thing, that is the energy in size, and the red thing, that is the dissipation. And you can see that they are in very different scales. So this is a useful problem. This is something where you can get knowledge of turbulence from. What we're going to do now is that we're going to extract a piece of the flow field, crop it, put everything else to 0, and to that piece we have to do that funny equation with what is telling you is that it belongs to a flow field, because if you extract it as this, it doesn't belong to any physical flow field. And when you do that, you end up with this, which is a piece of your flow field, a very small piece. And what I'm going to do with this is subtract it from the initial flow. So I'm removing it from the initial flow. And then you get something that is like this. I don't know if you remember that there was something there before, and now it's white. I remove a piece of my flow. Because this is a turbulent flow field, in principle we know that if we add a perturbation, it has to grow because it's chaotic. The question is that we want to run in time and see how it grows. And I want to mention and highlight that the answer is not obvious. It's not obvious what's going to happen with that perturbation. For example, here I have two cases that I run separately. In the yellow case, I remove 50% less energy than in the pink. The pink is something that is doing, in principle, much more harm to the dynamics of turbulence. But you run in time, and what happens is that the yellow one, after some time, is 6 times bigger. So there must be some dynamics close to where this perturbation was introduced that are making them grow 6 times faster. And the reason, the point of doing all these computations is, can we infer those dynamics from the data? In essence, it's like if we are the neural network, right? We have the data, and now we're trying to see if we can make some sense of this. For this, we had to run 1 million problems, because you need to test many initial conditions in many places with different sizes. I introduce a parameter that is the size. I have to play with that parameter. But you can run 1 million simulations because you have, again, this type of hardware, okay? We had too much data too. The strategy here was different. If you run 1 million of simulations, you don't have anywhere to store that data. In this case, what we did is use the CPUs, which typically people don't use, because you are just using your new device, and the old one you left it abandoned, okay? We didn't abandon it. We use it to read the data on the fly as the GPU is producing your simulations. You compute the things you care. I don't care about the whole flow field. I just care about how much the perturbation grows, where it's located, how the flow looks in the vicinity, and I can compute those things without ever storing the simulation to disk. And this gives you very nice efficiency. And now what we're doing is, of all those perturbations, that million of perturbations, see if we can distinguish the top 5% that grow the most from the 5% that grow the least. I have a classified data set because I run the simulations, and I know which pieces of the flow grow a lot, which are these. This is changing to a different example every time. It could be forever here for 1 million, and the same here, well, 1 million or 5% of 1 million. And the same for this one, okay? And the question now is, what can I measure here and what can I measure there that helps me distinguish one from each other without actually running the simulation every time? Well, you are seeing that they are different in size, they look different, so there are many things that you can measure. The idea is we measure all those things that we believe that make a difference, and then we try to classify them. And for this, there are many classifying algorithms. We're using one that maybe some of you are familiar with, which is a support vector machine. It's something very simple. You have a parameter that you believe that is a good classifier, and you compute the PDF of that quantity condition to be significant because you have a training data set, or to be insignificant. If you can separate the probability, means that you can decide a priori if something is significant or not. And if you cannot, like in that case, it's about classifier. By knowing that, you cannot guess if something is significant or not. Okay? And there are many things you can measure. There are many things you can try. We measured about 80 quantities. Most of them were not helpful, but some of them were. One example is the fractal dimension, which maybe is a weird concept, but it's something that you can compute that tells you the complexity of objects. It's something that looks like this. You put boxes in your complicated object, and you count how many boxes of each size you need to be able to cover the whole object. The typical example is this. I don't know why, but it's the coast of UK. If you move to smaller and smaller boxes, you count how many more you need when you get smaller. If the coast was smooth, in this case, you would need a power of 1 because it would be a line. But in this case, it turns out that you need more. For my objects, if they are three-dimensional and I'm counting boxes, in principle, I would need a power of 3 because they are three-dimensional. It turns out that they are not three-dimensional. So if you count the insignificants, that were the one on the right that look smoother, they have a power that is about 2. So they look like surfaces, whereas the significant are closer to 1. And I don't know if you remember, but they look like a bunch of spaghettis, okay? They look like a filaments tangled together, and this distinguishes them. And this is better than the size, it's better than the energy, because this is geometrical. It doesn't depend on any parameter, okay? And all this, is it useful? I'm going to try to explain to you in one slide, which is going to be a little bit hard, that this is useful. And for that, what I'm going to do is call an assimilation experiment. And I'm going to explain to you how this works. I'm going to take a base simulation. This is a normal simulation that I'm just using as input. This could be measurements from the atmosphere. It could be data from somewhere else. I don't care. I'm going to use all the classification that I just elucidated to estimate if things are significant or not. And this word is very important. I'm not running my perturbations again. I'm not computing my significance. I'm going to use the model I just envisioned, for example, the fractal dimension, to predict if things are significant or not. And I'm going to take the 10% that look more significant and more insignificant. And I'm going to feed this data to two different simulations. This one is getting 10% of the information for A. So it's getting 10% of the information of A in places where A is significant. And this one in places where A is insignificant. In principle, both of them know 10% of the energy and volume of A, but they know it in different places. And what we are going to see if this makes a difference. And it makes a huge difference. It's incredible how good this is. In fact, I have believed for months that this was wrong, but I promise you that it's correct, even if it's very good. Note that the maximum possible error is 0.9, because for sure 10% of the information I'm giving to those simulations. So in the insignificant places, you're getting very little else. Your flow is not mimicking the base flow at all. It's very close to the things that you are giving to it, and that's it. Whereas the significant is almost 50% correct. You're getting a simulation by just using 10% of the data that is 50% correct, in contrast to doing it wrong. So you can really get information about the dynamics by doing this type of experiments. So with that, my conclusions are, I'm going to summarize them. Basically, I hope I convince you that turbulence is complex, but that data on turbulence is useful to make reduced models. I hope I convince you to open now the manual of programming GPUs for your problem, because they probably are useful if you're doing PDEs. If you have a problem that is not a PDE, but it's a network that has a lot of degrees of freedom, they are useful. And in these models, if you know a few degrees of freedom that are important, maybe you can get consequences. So with that, well, thank you for coming, thank you for listening, and I'm happy to take any questions. Thank you.